Hopefully, it's common knowledge that on the surface of our planet, water can typically be found in its liquid state at, say, 80 degrees Fahrenheit, and that we have to heat this water up to 212 degrees Fahrenheit in order for it to transition from a liquid to a vapor, such as steam. Liquid refrigerant, on the other hand, will actually boil at 80 degrees Fahrenheit in an evaporator coil, just like our water boils into steam at 212 degrees Fahrenheit. But we can get water to behave like refrigerant and boil at 80 degrees Fahrenheit if we put it under a vacuum. We can also get refrigerant to behave like water and be a liquid at 80 degrees Fahrenheit if we put it under a lot of pressure. And that task is taken on by the compressor in our condensing unit, which takes the refrigerant from, say, 100 psi to a couple hundred psi. The problem is that when we increase the pressure of refrigerant, we're also increasing its temperature. So to get that refrigerant back down to ambient temperatures, we have to cool it off, which is the job of the condenser fan. Now, we don't have X-ray vision. We can't see through the copper lines to determine whether or not the refrigerant has completely turned into a liquid. And even with a sight glass, we still can't be 100% certain. But there is one temperature we can take to determine this with absolute certainty, and that is often going to be a subcooling temperature. Now, before we get to all that, why is it so important that our refrigerant is in a liquid state? Liquid refrigerant is what actually absorbs all the heat from the home. Refrigerant in its vapor form does absorb heat, but not nearly enough to cool a house down, so it has to be liquid, no exceptions. So what is subcooling, and why does it tell us with such certainty that refrigerant is absolutely in a liquid state? As refrigerant transforms from a vapor to a liquid, it's giving up a lot of heat. But in this process of giving up heat and going through this transformation, it's not actually changing the temperature of the refrigerant. The temperature of the refrigerant doesn't actually change until that transformation is complete and the refrigerant is completely liquid. Our high side pressure gauge can tell us at what temperature this transition process is occurring, where refrigerant is converting from a vapor to a liquid. So if we were to read just slightly over 300 psi for our 410A refrigerant, the transition temperature would be around 100 degrees Fahrenheit. So through our entire transition zone, the refrigerant is remaining at that temperature despite the fact that it's giving up heat. Now, if we put a temperature probe on our liquid line outside of the condensing unit, we can measure the temperature of the refrigerant at that point. Now, because we know it's not possible to lower the temperature of the refrigerant until it's completed this transformation from a vapor to a liquid, if we're reading below that 100 degrees with our temperature probe, then we can know for certainty that the only way that's possible is the refrigerant has completed its transformation. So if our refrigerant is going through that transition process at 100 degrees Fahrenheit and we measure 90 degrees Fahrenheit on our copper line, we know we've cooled the refrigerant down by 10 degrees, which only happens during the liquid phase. And that's our subcooling temperature, the difference between that transition temperature and the actual temperature on the line. Now, if we're still reading 100 degrees on our copper line, that means our refrigerant hasn't had the chance to actually cool down yet, so it may not be completing the transition process at that point. Sometimes this can be due to an absolutely filthy coil. If we don't have good airflow across it, we're not going to be able to pull that heat off to fuel that process. Another reason can also be the condenser fan motor itself is not running. We can also have a problem with a thermal expansion valve. If it's throttled wide open, we're not going to be able to maintain the pressures we need to liquefy the refrigerant, and so we can end up having the refrigerant flash back over to a vapor even though it's trying to condense to a liquid. Considering none of those things are the problem, we can actually use this subcooling temperature to charge a system. When we add refrigerant to a system, we can increase the amount of liquid refrigerant that's in a condenser, and that can give us a little more time to cool it down and increase that subcooling number to a point. You'll know you're overcharging a system when you keep adding refrigerant and your subcooling isn't changing anymore. That's a pretty good sign you may have missed one of the other causes for low subcooling. Now, what our subcooling temperature actually needs to be is usually determined on the data plate of the condenser unit itself. It'll literally tell you 8 degrees, 10 degrees, 12 degrees subcooling. Now, this subcooling method of charging a system is reserved for evaporator coils that have thermal expansion valves on them. If we have a fixed orifice, like you might see in older R22 systems, we generally go by superheat. Now, if you haven't seen it already, I do have a video on superheat. I will link it in the description below. Until the next one, happy HVAC, my brothers.